In this session, let us examine the behavior of a series RLC circuit connected across an alternating voltage source. In this figure, you can see that a resistance R, a capacitor C, an inductor L is connected in series to an alternating voltage source of frequency F. In order to recall the phasor relation between the current through different elements and the voltage across them is reproduced here. Here you can see that the phasor relation between the voltage and current in the case of a pure resistor, a pure inductor and a capacitor is reproduced here. And in all these cases, we have taken the current through that element as a reference. So the phasor corresponding to the current is drawn along the positive direction x-axis, that is the reference direction. And here you can see that the current through the resistor is in phase with the voltage across the resistor. And here you can see that the current through the inductor lag by an angle of 90 degree with respect to the voltage across the inductor. And here in this case, the current through the capacitor leads by an angle of 90 degree with respect to the voltage across the capacitor. And these are the same information is conveyed by these waveforms. Here you can see that the voltage across the current and voltage across the resistor and the current through the resistor is in phase. Here you can see that the current through the inductor lags by an angle of 90 degree with respect to the voltage across the inductor. And here you can see that the current through the capacitor leads by an angle of 90 degree with respect to the voltage across the capacitor. And this Xc is equal to 1 by omega C is the capacitive reactance of the capacitor, and XL equal to omega L is the inductive reactance of the inductor. And here you can see that if you apply Kirchhoff's voltage law equation to this law, you get an equation Et minus Er minus El minus Ec. All these quantities are vector representations or phasor representation. From here you get Et is equal to Er plus El plus Ec. All these are phasors. So here you can see that the total applied voltage will be the sum of the voltage drop across the resistor, voltage drop across the inductor, and the voltage drop across the capacitor. So finally we get an equation Et, the total applied voltage in phasor form, is equal to Er, the drop across the resistor, plus El plus Ec, that is the voltage across the inductor and the voltage across the capacitor. Here you can see that we have inserted El and Ec in parenthesis in order to make it clear. Here you can see that the voltage across the resistor and the current through the resistor is in phase with the voltage, which is shown in this direction, in this figure. Here you can see that this is the direction of the current or the reference phasor I. That is why it is drawn along the positive direction x-axis. And the drop across the resistance Er is in phase with the current through the circuit. So that is how we have drawn Er along the direction of I. And here you can see that this is the voltage drop across the inductor, and you can see that it is leading by an angle of 5 by 2 radians with respect to the current through the inductor. So this is El, and here you can see that this is the voltage across the capacitor Ec, and you can see that it is making an angle of 5 by 2 radians with respect to the current, and it is lagging with respect to the current. And if you sum up all this, here Er is this phasor, El is this phasor, and Ec is this phasor. So, and you can see that if you add vectorially Er, El and Ec, you get the applied voltage. So in order to add El and Ec, you can see that they are opposing each other. So the resultant will be in the direction of El, because here you can see that three conditions are there. Here you can see that El is greater than Ec. That means the inductive reactance is higher than that of the capacitive reactance, or the reactance of inductor is higher than that of the capacitor. That means as a whole, this circuit will be behaving as an inductive circuit. And here, in order to find the resultant between El and Ec, here El is from this point up to this. And you can see that magnitude of El is higher than magnitude of Ec. So the resultant will be along this direction, because El and Ec are in opposite directions, and the resultant will be in the direction of the phasor with the higher magnitude. So here El is greater than Ec, so the resultant will be El minus Ec, which will be leading with respect to the current through the circuit by an angle of 90 degree. So now you can see that the resultant Et is obtained by sum of this phasor Er and this phasor El minus Ec. Now if you add these two phases vectorially, you get the resultant as ET, which is leading with respect to the current through the circuit by an angle of theta. Now if you consider another case, here you can see that EC is greater than EL. That means the capacitive reactance is higher than that of the, or capacitive reactance is higher than the inductive reactance. That means as a whole the circuit will be behaving as a RC circuit because inductive reactance is lesser. So in that case you can see that this is the drop across the inductor EL and this is the drop across the capacitor EC, and the magnitude of EC is higher than that of the magnitude of EL. In that case the phasor sum of EL and EC will be in the direction of EC, and it is marked as EC minus EL, this phasor from this point up to this. Now the resultant of the voltage across the resistor and the resultant of the voltage across the inductor and capacitor taken together will be this ET, and here you can see that ER is the drop across the resistor and this is the resultant of the drop across the inductor and capacitor. So now the resultant or the total applied voltage ET will be given by the phasor sum of this ER plus this EC minus EL. Now you can see that the applied voltage will be lagging with respect to the current through the circuit by an angle of theta degrees as shown in the figure. Actually you can see that this is the applied voltage ET, but the current through the circuit is leading by an angle of theta degree in this case. And here you can see that because EL is greater than EC, current through the circuit is lagging with respect to the voltage signal by an angle of theta degree. Because in these phasor diagrams we have taken I as reference, that is why we have shown it as here, because here you can see that the applied voltage is lagging with respect to the current through the inductor by an angle of theta degrees. Now another case is there when EC is equal to EL. In that case the capacitive reactance will be equal to the magnitude of the capacitive reactance will be the same as the magnitude of the inductive reactance. In that case the drop across the inductor as well as the capacitor will be same. So the resultant will be, or the effect will be cancelled by each other. Here you can see that this phasor EL has the same magnitude as that of this phasor EC. So the resultant will be 0. In that case the total applied voltage will be ER, because this EL plus EC will be 0 in this case because they are opposing each other, and the resulting current will be in phase with the applied voltage. That is what is shown in this phasor diagram. Here you can see that the total applied voltage ET is along the direction of ER. So these three cases will be there in case of a series RLC circuit, and this particular case when XC is equal to XL, or the inductive reactance is the same as the capacitive reactance of the circuit is said to be in resonance. Now if you consider the impedance triangle as we have seen in case of RC and RL circuits, here you can see that the total impedance will be given by, this is the total impedance and this is the resistance and this is the reactance. And in both cases here you can see that three conditions are there. In two conditions, XL greater than XC and XC greater than XL, the impedance triangles are shown here. Here from the previous slide you can see that if you scale up, this is the case when XL is greater than XC. So this is the resultant phasor diagram. Here if you scale this phasor diagram with I, that means if you divide, this magnitude will be given by IZ and this will be given by I into XL minus XC, and this magnitude will be given by I into R. If you divide all these magnitudes by the magnitude of I, you get a impedance triangle as we have seen in case of RC and RL circuits. So here you can see that this is the total impedance of the circuit and this is the resistance, and this is the reactance. And the magnitude of the reactance in this case, when the inductive reactance is higher than the capacitive reactance, total inductance will be given by XL minus XC. And from here you can see that total voltage, this relation we have already seen, because VR is the voltage across the resistance and VL minus VC, because here you can see that VL is greater than VC, that is why we have taken VL minus VC in this case. So if you substitute VR is equal to IR and VL is equal to IXL and VC is equal to IXC, we get a relation like this. V is equal to I into root of R square plus XL minus XC whole square. From there we get a relation I is equal to V divided by this, or this will be equivalent to the impedance of the circuit. So Z is given by R square plus XL minus XC whole square. And if you consider this impedance triangle, here you can see that this magnitude, this is the resistor, and here this is the resultant reactance, which is given by Xc minus XL. In this case, Xc is greater than XL, that is why it is drawn in this direction. From here also you get the same relation. Z is equal to R square root of R square plus Xc minus XL whole square. And this is the equation for the impedance when XL is greater than Xc. And here this is the equation for impedance when Xc is greater than XL. But when XL equal to Xc, you can see that this term will be 0 and Z will be equal to R. In that case, if you consider the previous slide, when XL equal to Xc, the impedance of the circuit is minimum. That means the maximum current will be flowing through the circuit, and such a condition is known as the resonance. So when a circuit is in resonance, when a series circuit is in resonance, current in the circuit will be maximum and the impedance in the circuit will be minimum. Now if you find from the impedance triangle or from the power triangle, you can see that the phase difference between the voltage and current phases is given by tan inverse of X by R, where X is the difference between the inductive and capacitive reactances in the circuit. When XL is greater than XC, capital X will be XL minus XC, and the circuit will be inductive and the current will be lagging with respect to the voltage. And here when reactance or when Xc is greater than XL, the total reactance X is given by Xc minus XL. In that case, you can see that the circuit is capacitive and the phasor relation between the voltage and current will be in such a way that the current will be leading with respect to the voltage across, or voltage of the applied voltage by an angle of 90 degree. Current will be leading with respect to the voltage. In this case, current will be lagging with respect to the voltage. And here you can see that R is the resistance of the circuit. From this relation, if you calculate cos of the angle phase difference between the voltage and current, we get cos phi, which is termed as the power factor of the circuit, which is obtained by R by Z. It can be obtained from the impedance triangle. From here you can see that cos phi is equal to R by Z. In this case also it will be same, but it will have a negative sign when you compare the phase difference or the power factor in case of inductive circuit and a capacitive circuit. Now if you consider the power in an RLC series circuit, here you can see that the total power in a series RLC circuit, there are three components or three terms are there. If you find the product of the voltage and magnitude of the voltage and RMS value of the voltage and RMS value of the current, you get a term apparent power, as in the case of a DC circuit. In a DC circuit, you have only one term, which is power, which is given by the product of the voltage and current. You get the real power. But in case of a AC circuit, a term power factor comes into play. Here you can see that the product of the RMS value of the voltage and current will be, or it is termed as apparent power. And the term, when you multiply this apparent power with the cos phi, which is termed as the power factor, you get the real power, or the power dissipated as heat in the resistance of the circuit. And when this apparent power V into I is multiplied by sin phi, it is termed as the reactive power. And with all these different terms, a triangle can be formed, which is known as the power triangle in case of a RLC series circuit. And from here you can see that I square R is the real power that performs the work measured in watts, and generally, or it will be dissipated as heat in the resistance of the circuit. That is the general relation which we use in case of a power dissipated in a resistive circuit or in a resistor is given by I square R. Here I square is the RMS value of the current through the resistor. and the reactive power, which is measured in and was VAR, that is VA reactive, it is obtained by I square X. I square is the square of the RMS value of the current through the inductor, and the total apparent power measured by VI, it can be obtained as I square Z, or the apparent power, and generally it is expressed in volt amperes. These are the values or the equations for the impedances in case of different combinations of the circuit. In case of a pure resistive circuit, Z is R itself, and there is no phase difference between the voltage and the current phases. And in case of a pure inductor, the impedance is given by, or impedance will be equal to the inductive reactance given by XL equal to omega L, where omega is given by 2 pi f, where f is the frequency of the alternating voltage source, and this is the phasor relation. Here you can see that VL is leading with respect to I by an angle of 90 degree. And in case of capacitor, Z is given by XC, and the phase difference between the, or the phasor relation between the current and voltage is voltage lags by an angle of 90 degree with respect to the current. And in case of a RL circuit, impedance is given by root of R square plus XL square, and the total phase difference between the voltage and current will be between 0 and 90 degree, and the current will be lagging with respect to the voltage phasor by an angle of phi, which is less than 90 degree. And in case of an RC circuit, the impedance is given by root of R square plus XC square, and the magnitude of the phase difference between the voltage and current will be in between 0 and 90 degree, and the current will be leading with respect to the voltage by this angle phi. And in case of an RLC circuit, depending upon whether XC is greater than XL or XL is greater than XC, the equation for the impedance will be given by square root of R square plus the difference, square of the difference between XL and XC. That will be the expression for impedance, and the phasor or the current will be lagging or leading with respect to the voltage depending upon the difference between the magnitudes of XL and XC. In this case, when XC is greater than XL, the current will be leading with respect to the voltage, and in this case, when XC is less than XL, the current will be lagging with respect to the voltage by an angle phi. And in all these cases, we have seen, or we have considered, the frequency of the voltage source as constant. Now, if you consider a voltage source with a variable frequency, and here you can see that L and C will not be varied, but if you change the frequency of the alternating voltage source, the inductive reactance and capacitance, capacitive reactance get varied because they are depending upon the frequency. Equation for the inductive reactance is given by 2 pi FL. Here you can see that the inductive reactance is in direct relationship with the frequency. That means when the frequency increases, inductive reactance increases. And here this is the equation for the capacitive reactance, and it is given by 1 by 2 pi FC. Here you can see that the capacitive reactance is inversely proportional to the frequency of the voltage source. That means when the frequency increases, XC will be getting decreased, and when the frequency decreases, XC will be higher. So the variation of the inductive reactance with respect to frequency is plotted here. Here you can see that as F increases, XL increases. But here, this is the plot of the capacitive reactance with the frequency. Here you can see that when the frequency is less or smaller, the capacitive reactance is higher, and as the frequency increases, you can see that frequency is in the denominator. So when the frequency increases means the capacitive reactance get reduced. And in case of a series RLC circuit, if you plot anyway, there is no resistance is not depending upon the frequency. So if you consider a series combination of L and C, and if you vary the frequency, here you can see that at a certain frequency FR shown in this figure, the inductive reactance will be the same as the capacitive reactance, and that is the condition of the resonance in the circuit. Here you can see that at this point, the inductive reactance will be the same as the capacitive reactance. That means the drop across the inductor will be cancelled by the drop across the capacitor. That means in case of an RLC series circuit as shown here with a variable frequency voltage source, the drop across or this drop VL minus VC will be 0 at this particular frequency, and that frequency is known as the frequency of resonance, and at that frequency the current through the circuit will be maximum here, because you can see that at that particular frequency or at resonance frequency the drop across this L and the drop across C will be getting cancelled. That means in effect between these 2 points a short will be there. A short is there means no resistance or no drop across the element, and the total current will be given by the magnitude RMS value of the voltage divided by the resistance. That will be the current passing through this circuit at the time of resonance, and that will be maximum because the total impedance of the circuit at resonance frequency is lesser, because there is no imaginary part in the impedance. Impedance Z is given by R, because XL minus XC will be 0 in that case, and this particular frequency is known as the frequency of resonance in case of a series RLC circuit. Now here you can see that the phase difference between the voltage and current when the frequency is varied. Here you can see that below the resonance frequency the circuit will be capacitive and the current will be leading with respect to the voltage, because here you can see that at lower frequencies the inductive reactance capacitive reactance will be higher, and in case of a series RLC circuit the circuit will be behaving as a capacitive circuit, so the current will be leading with respect to the voltage by an angle theta. And at frequency F is equal to Fr, that is at resonance frequency there is no inductive and capacitive reactances, because the drop across those elements will be getting nullified and the current will be in phase with the voltage. And you can see that at resonance frequency current in the circuit will be in phase with the voltage, and at frequencies above the resonance frequency inductive reactance will be dominating with reference to the capacitive reactance, or the inductive reactance will be higher than that of the capacitive reactance, and as a whole the circuit will be behaving as an inductive circuit, and you can see that current will be lagging with respect to the voltage by an angle theta. And here you can see that as we have seen, the condition for resonance is given by XL equal to XC at that particular frequency, and the expression for XL is omega L and expression for XC is 1 by omega C, where omega is given by 2 pi F. So from here in this relation you get 2 pi FL is equal to 1 by 2 pi FC. From there we get the frequency of resonance is equal to 1 by 2 pi into root of L's. Thank you for listening.